This beautiful lecture series. So, Professor Pisier, please.
Okay, thank you very much. Thank you. So, as you know, I have concentrated on lifting properties up to now, and I've emphasized that it's a little bit curious that lifting questions are connected to extension problems without dualizing, directly without dualizing, just on the same diagrams. So now I want to go through notions related to the extension property, and in other words, injectivity. So I remind you how it goes. So this is now an extension problem instead of a lifting problem, right? So we say that X, our target X, which can be a C-star algebra, but just more generally an operator space, is injective if anytime we have a completely bounded map with range in X, then and there is a larger domain, it can be extended to the larger domain, preserving the CB norm. So the CB norm of the extension U tilde is the same as the CB norm of U. And of course, since this Y1, this larger operator space Y1 that contains our domain Y is itself an operator space, we can think of it as realized inside B of H, okay? So we can think of Y1 as sitting in between Y and B of H. So we can actually just concentrate on B of H, and you can look at just the second diagram as the definition of this extension property. So X is injective if we have the extension property like this. So the fundamental example is B of H. So if X is B of H, then this extension property is true. This is a very famous theorem due to Arveson, which is called non-commutative Hahn-Banach theorem, because what was known before, well-known result of, I think, goes back to Nachbin, is that if X is an L infinity space over any measured space, then it has this property for the ordinary norm. So this is the commutative case. And this was already a generalization of Hahn-Banach corresponding to, of course, the case when X is one-dimensional. So we now have a Hahn-Banach non-commutative for maps with range in B of H. We know they extend. Now let me pass to a generalization. Generalization of injectivity is the weak expectation property. So I propose to look at it like this. In this screen, I put things in parallel. It's important to see how weak expectation property that I want to introduce now is parallel to injectivity. So first, let's look at an equivalent formulation of injectivity. So now, watch out. Now I'm looking at this extension diagram, but when X is the domain. And I'm saying that it's going to be true that any completely bounded maps from X to Y extends to B of H with preservation of the CB norm. This is true now. There is a subtlety here that you have to catch. This is true because if X is injective, and you can sort of go back from one diagram to the other, if X is injective, that will tell you that it is complemented inside B of H by a projection of CB norm 1. So if you have a projection, I hope you're seeing my arrow, if you have a projection like this, as I'm indicating, from B of H to X of CB norm 1, then this extension U tilde can just be the composition with the projection, okay? And you can easily, it's an easy exercise to see that if you have this, and if you know Arveson's theorem, you know B of H is good, then you can go back to extension property as before. So that's another way to look at things, okay? It's a different diagram, watch out. But that brings me to a good, presentation of the weak expectation property. Weak expectation property is the same thing, but now prefer to look at a C-star algebra, but that could be an operator space. I look at a C-star algebra, and I take this Y to be a von Neumann algebra. Okay, so the Y is a dual space, so this is special. And then I'm saying, okay, I can find an extension from B of H to the von Neumann algebra with the same CB norm. So this is obviously a weaker property because the diagram is now restricted to maps with range a von Neumann algebra, a dual C-star algebra. So that's definition of the weak expectation property, but there is another way to look at it, which is perhaps clearer, which is but a little more abstract. You see my screen changing, right, Parasa? It's not like yesterday, I hope. It's good?
Yeah, it's good. Yeah.
It's good. Okay. So this second presentation of the weak expectation property, which I formulate as a proposition, is that your C-star algebra A has the weak expectation property, and the A we are looking at is sitting inside B of H as a sub C-star algebra. If and only if there is a contractive linear map from B of H to the bidual of A, so the bidual of A, which it's not a projection, it's such that it is the identity when restricted to A. So in other words, you see T restricted to A is the same as the canonical inclusion of A to the bidual. Okay, so there are many here details, many decorations that I could make to this statement. So I could have stated it with, I state it with contractive for T, but I could state it with completely contractive and completely positive, because there is a famous theorem of Tomiyama that says that in such situation, theorem of Tomiyama is famous for projections onto von Neumann subalgebras, but it will apply here. It says that if it's contractive, it's automatically completely positive and so on. So this applies here. The map T will be automatically much better, okay? But I phrased it with contractive. Now, these maps T are the origin of the name weak expectation property, because such a map T is what is called a weak expectation. And you see, it's a curious map. The map on the diagram that you're seeing here, okay, goes from B of H to bidual, is the identity on A. And then if you just take the double dual, okay, you take the double dual of this map T, so you will have a map from B of H double star to A double star, and then you have a canonical embedding now of the bidual of A. You're basically taking the double dual of everything, but of course your double dual of A is nicely embedded, as I'm sure you know, into the fourth dual with a nice projection. So I can anyway go into the bidual. Or you remember that, well, there is okay, this is something I wrote, which is not quite correct. I meant to write here, sorry, I meant to write here, not T star star. This is incorrect. I'm sorry. I slightly fumbled. This should not be the T star star. It's not what I meant. The T star star, I'm very careful with these things, goes into the fourth dual. But this is, instead of T star star, this is the canonical extension of this T to the bidual. I told you that the bidual has a universal extension property for maps into dual C-star algebras, in other words, von Neumann algebras. So I use this. This is the canonical extension of T, okay, using weak star limits and so on. So that's a natural map. And this new map is a projection from the bidual of B of H to the bidual of A double star. So in fact, that can be phrased as a characterization of the weak expectation property. You could say the weak expectation property means that the bidual is sitting inside the double dual of B of H, bidual of B of H, with a projection of norm 1 or of completely bounded norm 1. But unfortunately, it has to be slightly corrected, because that's a too general class, what I just described. It has to be that the embedding of A inside the bidual must be the bitranspose of the embedding of A into B of H. If it is this embedding, then what I said, the existence of a projection onto it, is equivalent to the weak expectation property. So you see, that's nice, because here, of course, I assume that you know this. When we have when we have the extension property, our space X, if we take for U in the extension property, if we take for U the identity of X, this is the classical observation, the identity of X, then U tilde will be a projection of B of H onto X of CB norm 1. And this formulation, of course, is equivalent to injectivity. So injectivity is existence of projection of norm 1 from B of H to the space, and weak expectation property is like this, provided the bidual is embedded in the bidual of B of H by the bitranspose of an embedding. The reason I insist is that if you don't say by the bitranspose of an embedding, then the property will characterize, it's very strange, it will characterize quotients of WEP C-star algebras, for which, well, except for the problems around the cone embedding problem, no counterexample is known. Okay, so of course the observation is that weak expectation property contains a strange class, which is the union of nuclear C-star algebras, which of course are separable, and injective phenomenon algebras. Okay. So it's important to know the connection with nuclearity. So now a C-star algebra is nuclear, as I'm sure I probably mentioned it before, but you've heard of it. If simply the minimal and maximal tensor product coincide of A with any other C-star algebra B, any B C-star algebra, we have this uniqueness of C-star norm, and this class has a lot been studied a lot. There's a lot known about it. In particular, there's a very beautiful connection with injectivity through the work of Choyev-Ross that used a lot of the advances of Alan Cohn. That C-star algebra is nuclear if and only if simply the bidual is injective. So as for groups, I pointed out here that amenable groups are really the best of groups for all these properties. Amenable groups gives you C-star algebras that have all the properties. So C-star G is nuclear, C-star reduced is nuclear. In fact, they are coinciding when G is amenable. This is the same C-star algebra. And this is the same as saying that the phenomenon algebra generated by the reduced is injective. Hello? Yes? Question? No. Okay. So some reformulations of injectivity are interesting because they lead to some open questions. That's why I want to mention them here. So an operator space is injective if and only if there is a projection with CB norm 1. This is what I just explained when I returned to the first screen. When M is a phenomenon algebra, Tomiyama proved that it suffices to have a projection of norm 1. It will automatically be completely positive and CB norm 1. But a strange question that remains open is, suppose you have a projection which is just bounded from B of H to M. And this is something that intrigued me many years ago, and it is still open, I think, I'm pretty sure. What I could prove is that if the phenomenon algebra tensor product of M with itself, so this is This means the von Neumann algebra tensor product. Okay, I'm not respecting my own conventions. The von Neumann algebra tensor product is somehow the algebra is isomorphic to its square, tensor square. If this holds, then there is a trick, and you can show that if it's, if there's a projection with bounded, which is bounded, which has finite norm, then there is a projection with norm 1. You can sort of guess maybe the kind of, multiplicativity trick, but it requires an argument. So the other thing which is known is that if you put completely bounded, if you look at completely bounded projection, then if you have a completely bounded projection, then indeed it forces injectivity. Projection is not automatically, of course, is not automatically of norm 1, this is clear, but some other projection of norm 1 exists. So this is something that we proved independently of Christensen-Sinclair. Now I come to the famous cone embedding problem. And I warn you that, the situation is sort of in some kind of limbo, because it now has been 2 years that there is a 200-page preprint, which comes from a group of people working in quantum information theory, computer science, and sort of complexity, say, and who have managed, as they say, to show that the answer to this cone embedding problem is negative. And probably this is correct, as I said, but we still need to have somehow a verification by operator algebra people. Incidentally, the connection with quantum information theory goes through a reformulation of the cone embedding problem in terms of something called the Tserelson problem. But the Tserelson problem, in my view, is somehow can be related. This has been done by workers in the field to the Kirchberg formulation. So I will present the Kirchberg formulation in a minute, and ignore for these talks the Tserelson formulation, but it's closely connected. That's what you should know. Okay, so this is a very amusing story, because this is a problem that is currently certainly the biggest open problem in operator algebra theory, and it was raised by Alain Cohn really in passing in his very famous 1976 paper on injective von Neumann algebras. He observed that the free group, which is normally the bad apple, definitely the free group for Neumann algebra is non-injective because free groups is non-amenable. So as I just said, it follows von Neumann algebra is non-injective. But nevertheless, the free group satisfies a good approximation property by matrices, of over finite dimensional Hilbert space. So matrices, finite dimensional matrix algebras provide a good approximation of the von Neumann algebra of the free group. And so there is a small remark in Cohn's paper where he said, well, maybe this is so for any von Neumann algebra. Actually, I don't have a counterexample. And that's what started the story. So what's the problem? You look at the von Neumann algebra and you assume that you have a finite normal trace. So that's the very classical functional to consider on a von Neumann algebra. You assume that you have a trace, so that's like a non-commutative probability, which is positive, weak star continuous, and it satisfies the trace identity like ordinary traces. Trace of xy is equal to trace of yx, as it is written here. So that's a positive functional. So the question is,
for a second.
What? Yes?
May I interrupt for a second just to clarify an issue?
Sure. Of course.
That von Neumann algebras are injective as Banach spaces. Is that true?
Commutative ones are injective as Banach spaces, but not the non-commutative ones.
No, but then it's already a dual space.
I'm sorry. I'm not following.
Dictionary says that the duals are always complemented in their biduals. as Banach spaces.
Yes.
So
Yes.
any polynomial algebra, whether commutative or otherwise, will have to be injective as Banach spaces. Is that true?
No, there is something, some sort of confusion. No, because to be injective as Banach spaces, you have to be complemented inside an L infinity space, okay? Inside an object which is the universal injective Banach space. So that's L infinity. But so if you just, as you're describing, if you just go to the bidual, that produces a projection of norm one, but from, your tridual, which is which doesn't force anything special.
But I mean, as a dual Banach space, it will be injective, I suppose.
As a dual Banach space, I'm sorry, I don't follow. Don't follow. No, I'm afraid.
But I mean, they are duals. They are duals of certain pre-duals, and therefore they have got to be injective as Banach spaces. I mean, I suspect.
I think, Parasar, you're thinking of some property which is weaker than injectivity, or it depends how you're defining what you call activity as Banach spaces. But in the in the traditional definition, very few spaces are injective as Banach spaces, because they're going to be sitting in L infinity with a projection of norm one. And so, that's in fact that it's known what they are. They are C of K spaces with K, it's connected in a certain way. Very restrictive, very restrictive.
All right. Okay.
If you say dual, then that's going to be L infinity spaces actually.
So, but then they are complemented in their biduals. That means triple dual.
Okay.
Polynomial algebra.
Okay.
Professor Sophie, you can continue it after the talk. I mean, so
yeah, because I got a little, it got messed up for me. I mean, while I was trying to make sense of.
Sure, please. Yeah.
Okay.
Yeah, so, it's reasonably clear now.
Okay. So yes. So we have a finite normal trace on M, which is given to us, abstractly, and then on a discrete group there is a classical definition on the phenomenon algebra of a group. You have such a trace tau. So this is all over the place in phenomenon algebra theory, such functionals. And the question is, can they always be approximated by matricial trace? So traces, just acting on the usual matrix algebra and being the usual trace. So this is what I denote by trace n. This is the normalized trace, this TRN, that's the normalized trace. And so then the question is, in what sense do I say that the trace is approximated? So it's approximated in the following sense. This is the sense that corresponds to Kahn's question. Let's first say this. So without anything more, just like 1976, the question is this: you should have the following approximation for any epsilon, for any n, and for any n tuple in the unit ball of M. The question is, can you find an n tuple in the unit ball of matrices with a certain large but finite trace, which do the approximation in the following sense, that anytime you take a monomial combination like this of your n elements, so for instance, you could take something of length 5, and then all you do is that you put some stars somewhere, and somewhere you don't put stars. This is what the symbols psi1, psi-k explain. So then the question is that this thing should be approximated by the same thing, where you just have replaced x1, xn by certain chosen approximations given in advance in the matrix algebra. And then you request these approximations, x prime 1, x prime n, to be good no matter what for all the monomials that are here, but you have a restriction. You put a restriction on the degree of the monomial. So in other words, for any epsilon and for any degree of the monomial, you can find these X primes that do the approximation like this. You know, your trace is approximated by the other trace for all choices, for all places of the star. So you have an example, which is this, to give you an idea. But actually, I can drop this complicated definition immediately, because one of the results, very nice results of Kirchberg on this problem, is that he showed that you can actually restrict just to 2. So if you just have length 2, if you just have the approximation like this with xi star xj, I don't have to put it in the other direction because we are dealing with trace, okay? So tau of xi star xj should be close to the corresponding trace of the matricial approximations. This is enough, okay? So Kirchberg's equivalent formulation of the Kohn embedding problem is very striking. It is that this problem of Kohn concerning, you know, all traces, finite traces on phenomenon algebras, is simply equivalent to the assertion that the full C-star algebra of the free group on 2 or infinitely many generators, I prefer to use infinitely many generators because that's a nice universal object, it's equivalent to saying that this algebra has the weak expectation property. And in fact, this is equivalent, its formulation is perhaps even more striking. It's equivalent to saying that any C-star algebra is a quotient of a weak expectation property algebra. And a quotient of a weak expectation property algebra is, of course, called QWEP for short. The implication from this side to this side, so from left to right here, from the WEP assertion to the QWEP, this assertion is obvious because any separate, or almost obvious if you like, any separable C-star algebra is a quotient of the algebra C, which is here. So if C is WEP, any separable C-star algebra will be QWEP. And in this context, you can the separability by some simple tricks. So you end up with star algebra, and which until this, and now is considered, you know, solved negatively. But by the way, they solve the problem negatively by showing that there is a certain identity of minimal and maximal tensor products which does not hold, because one norm is computable in, roughly one norm is computable in polynomial time, the other norm is not computable in polynomial time, therefore the identity cannot hold. But they are not producing an example. So they are not producing an example of a C-star algebra which is not QWEP. That would be a phenomenon algebra, would be the same as a phenomenon algebra failing the Kohn embedding problem. Okay, so let me here present a little bit where I'm heading in the rest of the talk. So I remind you that the C-star algebra here, which is the critical object, is the prototype of a C-star algebra with local lifting property, and in fact, global lifting property. And motivated by this, in fact, we constructed a few years ago, Invenciones, this our Invenciones paper, a C-star algebra that I want to refer to, you know, in the talk. So I give it the name script A, and I'll explain very quickly at the end how it is fabricated, which is both LLP and WEP. And I will also say what this means, you know, soon. This algebra script A is locally equivalent to C, which implies, it's a little bit stronger than that, but it implies that each algebra, script A and script C, embeds in an ultra product of the other. So in the sense of finite dimensional subspaces, the algebra A is very close to the algebra C, and it is LLP and WEP, which means that it is exactly what we like for this prototype algebra? No, and now we think we know that it is not that I've taken and that I'll explain in the last screen is that I think that the construction that I have for these algebras is very much finite dimensional. In fact, I think it is so finite dimensional that I believe it can provide a counterexample to the implication local lifting implies global lifting. But unfortunately, I haven't been able to do that. But I want to now explain to you this subject. So the analog of Grothendieck's problem for C-star algebras was, of course, raised by operator algebraists. So in the 70s, Chris Lance asked the natural analogous question. He asked whether, if you have a C-star algebra A and you assume that the minimal and maximal tensor product coincide on A opposite tensor A, let me come back on A opposite, then does it follow that the same is true when we replace the opposite algebra by any C-star algebra? So in other words, whether this forces the algebra to be nuclear. So just very much analogous to Grothendieck, except that in the C-star algebra setting, the real natural choice is not so much A tensor A, but it's better to actually ask this for A up tensor A. Actually, the answers turned out to ignore completely that, because the solution to this problem was true for both pairs A or A up A. It turned out it didn't matter. But the choice of A up is very natural, because when you have a tracial state on a C-star algebra, you form immediately an L2 space associated to this trace. And you know that you have a left action and a right action of the algebra by left multiplication or by right multiplication on your L2. And if you now go back to representation theory, you see that that gives you the multiplication on the left naturally gives you a representation of A acting on your L2 space. But multiplication on the right, this is this thing about products on the right, that it gives you a representation, except that it flips the products. So it is a representation of the opposite algebra, which is just the same algebra, everything the same, except that the product of xy now is meant to be yx. The old yx becomes the new xy. Okay, that's the opposite. Okay, so anyway, and it's a rather involved example, which just for experts I mentioned, this is constructed as an extension of the Cohen algebra of the reduced C-star algebra of the free group. So he's using the Cohen algebra, and my example will also use it. But my example is new and a quite different counterexample. And his example was a solution to this problem, but it is not an algebra with WEP. It's not an algebra with LLP, sorry. So recall that we've denoted script C and script B for what I call the fundamental pair. And I remind you that we had that the pair, this is Kirchberg's fundamental theorem, that the pair script C, script B is nuclear. So more generally, what is true is that anytime you have a C which is LLP and a B which is WEP, then the pair is a nuclear pair. And this is somehow more or less easy to see, because your LLP algebra will be locally factorizable. This ordinary C being LLP will be locally factorizable through script C. And if B is WEP, locally, that is up to the bidual, this B will be factorizable through B of H. So that's the idea anyway. From this simple idea, you can get that, well, the pair will have to inherit the property of this pair. And so any such pair, LLP, WEP, is a nuclear pair. But what you have to remember is that the prototype of LLP is script C, while the prototype of WEP is B. So let me go to tensor product characterizations of LLP and WEP. So the first one we've already proved, if you recall what I did yesterday. A is LLP if and only if the pair A B of H, A script B, is nuclear. And I could also put here, excuse me, the algebra boldface B that is the direct sum of the MNs. The WEP analog of this is that a C-star algebra is WEP if and only if the pair it forms with the script, the algebra script C, is nuclear. So you see this beautiful symmetry, or this beautiful sort of duality that appears between properties WEP and LLP. So B is LLP if and only if AB is nuclear for all A WEP, while A is WEP if and only if AB is nuclear for all B LLP. And incidentally, I think I should have said this earlier, but the tensor products minimal and maximal, you know, are commutative in the sense that you can the flip isomorphism of the algebraic tensor product A tensor B to B tensor A that flips the factor. This identifies, you know, the min tensor product of both sides and the max tensor products of both sides. So anything I say for, you know, involving nuclear pairs for AB, the same thing is true for BA. There's no change. Okay, the pairs are not ordered. Now, this we have already said, right? If A is WEP, B is LLP, then the pair AB is nuclear. We have this. So now suppose that it is the same algebra. So assume A is both WEP and LLP, then this implies from what we just said that A tensor A min is equal to A tensor A max. And so this explains my interest in this situation, because if I can construct, and this is exactly what I've been doing, an algebra script A, which then I have a new counterexample to this sort that this is non-nuclear. Because of course, nuclear is the trivial case. If your algebra is nuclear, you know min equal max with anything, in particular itself. Okay, and here A op doesn't matter because it is easily seen that WEP and LLP, you know, pass from the algebra to its opposite. This is the same for the algebra or the opposite. So in fact, it plays no role. Now, what I always like to do is sort of look at things a little bit, you know, in retrospect. Historically, this is sort of amusing. So I wanted, but my skills with the computer are not good enough. I was hoping to actually show you a page of Kirchberg's paper, because this is very nice. At the end of his paper, he goes to a lot of pain in, you know, explaining a set of conjectures, actually several sets of conjectures, and, you know, a bunch of 8 on A, and another group that he groups as conjectures B. So B1, B2, B3, you know, and then A1, A2, and so on. And let's cut short. And main conjecture A is that the pair B, so B of H, just B of H, is a nuclear pair, while the conjecture B is simply that the pair CC is a nuclear pair. And then he shows that conjecture A is equivalent to the implication WEP implies LLP, while conjecture B is equivalent, this he shows, to the implication LLP implies WEP. So actually, at the time, he conjectures that WEP is very surprising, perhaps now, conjectures that they are actually the same property. And you know, so which probably has something to do with the things that I, you know, underlined, that this lifting relates to extension and conversely. So anyway, conjecture A was soon disproved. This is by Junger and myself in a paper in GAFA in 1995. We simply showed that indeed B of H fails the local lifting property. So the pair BB, if the pair BB is nuclear, with the previous presentation, you know that it means that B should be LLP. And this is what we disproved. B is not LLP. While the other conjecture B, well, Kierkegaard shows this is equivalent to the cone embedding problem. And so this, of course, remained open until, you know, this preprint I've discussed. There is a nice thing that I think should be mentioned about the pair A op A, which is the following theorem. This is a result of Hagerup, which is actually a rather delicate result, which is unpublished, but you can see it in my book at the end of my book on tensor products. And it says that a C-star algebra has the weak expectation if and only if the min and max norm coincide, but on A op tensor A, but on a certain special cone of tensors, which is the cone of tensors that are like this, positive definite. Okay, so elements in the tensor product that are of this form, I call them positive definite tensors. And the fact that this result is true explains the difficulty we had with Junger, you know, to show that. To show what we did, which is that we showed that B of H fails this equality for some tensors. And the difficulty is that because of what is here, B of H is injective. So B of H has WEP. So B of H satisfies this. So you see, this identity of min and max norm is satisfied by the tensors which are too good. And we had to sort of find the kind of the so-called pathological tensors that, you know, avoided this situation, because this holds in B of H for A equals B of H, that B of H being the prototype of WEP. Okay, so now let me go to discussion of the example. So suppose I have two operator spaces Z and Z prime. Let me say that, well, this is classical, right? Z prime is completely 1 plus epsilon isomorphic to Z if there is a linear isomorphism V between the two, such that the CB norm times the CB norm of the inverse is at most 1 plus epsilon. So I'm not sure I'm using this, but I will abbreviate this by Z prime isomorphic to Z with a 1 plus epsilon above. Yes, and then I say that A locally embeds in another C-star algebra C if for any epsilon positive and any finite dimensional subspace, so local always reflects to finite dimensional, there is another finite dimensional subspace in C, in the other algebra, which is 1 plus epsilon isomorphic to the original one. So whenever I have a finite dimensional subspace of Z, I can find an almost copy finite dimensional in C that copies the original one. And then I'll say that A and C are locally equivalent if each locally embeds in the other, which is perhaps not a good term, but anyway, that has the advantage to be quick. Let me show you here something which is quite important. If A has simple actually, if A has the local lifting property, that's a corollary of the characterization of the local lifting property, then A locally embeds in script C. This is simply a consequence of the universality of C, right? We can take A separable for simplicity. It's true in the non-separable case, but let's take A separable, and then we realize A as a quotient of script C. So then we can look at, this is an abuse, but essentially the identity of A is represented like this as a map from A to this quotient, because I have an isomorphism. So I write the isomorphism, I call it identity. That's the abuse, but I think it's clearer on the diagram. Then I take an arbitrary finite dimensional subspace, and the local lifting property tells me that there is a V that lifts the diagram and which has CB norm 1. And so, you know, that V embeds now E into C. I have the subspace V of E, which is a copy of E. And if you just trace back the maps, you see that since V is a complete contraction and Q is a star homomorphism that has completely bounded norm 1, that new subspace V of E inside C is, in fact, one isomorphic to the original space, because here this is true with epsilon equals 0, even 1 plus epsilon isomorphic with epsilon equals 0. But certainly it locally embeds in C. So what we did with Junge to show that the weak expectation property does not imply a local lifting property is simply we proved a more general fact that there are C-star algebras with WEP, no big deal, just B of H, which do not locally embed in script C. And so they must fail the local lifting property by the preceding statement, okay? So let me recall the preceding statement is local lifting property implies it embeds locally in C. So, you know, that's points out to what we did, which is that simply B of H, if we can show B of H does not, B of H fails local lifting property. Now, the curious thing is that if this is somehow the critical obstruction, because if you assume that A locally embeds in C, so which is more general than LLP, then it works. If A has the WEP, then it has the local lifting property. And so in that case, with the extra assumption, the implication proposed by Kirchberg in his conjecture A is true. Okay, so the main result that I have with this algebra script A is that there is a non-nuclear C-star algebra which has both WEP and LLP and is locally equivalent to script C. So in fact, what we construct is a WEP. We concentrate on WEP, but the difficulty that we have is that we must force it to locally embed in script C. This is the difficulty, to have at the same time that constraint. If we manage to locally embed it in C, then the preceding proposition, tells us that we get in the end the local lifting property, because if we locally embed in C and we have WEP, then we have local lifting property. So this is the procedure we use to construct the example. Now, that algebra, the way I'm describing it, will automatically be non-nuclear, because it is known that if you have an algebra such that C locally embeds in the algebra, then it cannot be nuclear. Script C does not locally embed in any nuclear C-star algebra. So our algebra will be definitely non-nuclear. In fact, there are lots of refinement. If just the linear span of the generators of the free generators, the free unitary generators that are, you know, a canonical object in script C, if this subspace does not locally embed, and it can be refined in many ways, then that's an obstruction to nuclearity. Okay. So the sketch of the construction is like this. What I I cannot go into detail because actually it gets rather tricky, but what I was hoping to show you, which of course gave me a great satisfaction, although it was 40 years later, is that I could inspire myself from the construction of the counterexample to Grothendieck's problem. And in terms of a framework, the framework of the construction is similar to the framework of the construction of the Banach space example, but the details are quite different and the technical difficulty are quite different. Because of course the difficulty here is to produce an algebra. So managing to have an inductive limit of linear subspaces, finite dimensional operator spaces. So this is what is used here. The ENs in our inductive limit are finite dimensional operator spaces embedded by a map Tn into the next space. So we have a sequence of finite dimensional spaces and a sequence of maps Tn, which are going to be 1 plus epsilon n embeddings. And this epsilon n is going to have to go to 0 sufficiently fast. So that's the basis of the construction. But then, so they need to be 1 plus epsilon, isomorphism. But then we also need that, we are aiming at multiplicativity. So we need to be able to do sufficiently many products. So we need this second condition here. And the third condition, I couldn't explain this, it take too much time, is that the multiplicativity of the map Tn will be also approximately multiplicative, but it will be approximately multiplicative with a rate that will have to increase very, very fast in such a way that this series, all this, we produce a C-star algebra as the inductive limit. And this C-star algebra is going to be nicely WEP if we can do the property number 4. And the property number 4, this is the thing which is analogous to the Banach space situation. If you remember the lecture yesterday, property number 4 is that the map Tn, which passes from En to En plus 1, improves from the minimal tensor product to the maximal tensor product, essentially just with the loss of epsilon n. The difficulty is that I cannot here take coefficient in the whole C-star algebra script C, so I do not get immediately the property that I want, but I can do this gradually. I can take in the algebra script C, a nest of finite dimensional subspaces with dense union, and then incorporate in the inductive construction that we do this at the nth level just for this subspace C prime n, which is not the whole algebra C prime, but a finite dimensional subspace. And then why are these primes here? So the prime is because I need to replace the algebra that is my interest, since I'm aiming at WEP. So I want to show script C tensor A be the same for min and max. Okay, so this should be really here script C, and it is only script C prime that is put here. It turns out it doesn't matter. C prime, the C prime is the so-called cone algebra associated to C. And cone, this is C-O-N-E, nothing to do with Alain Cohn. So this is just the tensor product with script C of the C-star algebra of continuous function with which vanish at 0 on the closed interval 0, 1. And continuous functions, so the tensor product with C, or equivalently, the algebra of continuous functions on the closed interval 0, 1 with values in script C that vanish at 0. So this is an object that is critically used in K-theory of C-star algebras, of which, quite frankly, I know very little. But it turns out that that was the critical tool to obtain multiplicativity of the maps. So to conclude the talk, I think I can maybe steal like a couple of minutes. Let me show you. This is very important for the way I've organized the talks. So I really wouldn't like to miss that. Let me point out to you, apart from conjectures A and B, a second statement that appears in Kierkegaard's paper and that he makes, which is that conjecture B, which is the cone embedding problem, implies the validity of the implication local lifting property implies lifting property. Now, this fact for us now, with all the reviews that we've made on the tensor product formulations for local lifting and lifting, this fact is very easy. So I really wouldn't like to miss showing it to you, because the first easy fact that you can sort of probably accept without objection is that if an algebra script C is WEP, so this is what is conjectured, that's the cone embedding problem in Kierkegaard's formulation, then, but that implication is for any C-star algebra, then the algebra L infinity of C is also WEP. So it's not totally obvious because that's not a tensor product, right? L infinity is non-separable, but this can be shown. It's sort of easy to believe. So if A has the LLP, the pair A L infinity C is nuclear, because L infinity C, that's our assumption, is going to be WEP. So we have this first identity. You see, min and max coincide on A L infinity C. But now also just the single pair AC, C itself is WEP, we remember that. So the single pair AC is nuclear, so it's such that min and max are the same. So I can write the first line because L infinity C is WEP and A LLP, and the second line because C is WEP and A LLP. But now you see the two lines together tell us that for our criterion for the lifting property that was at the end of the last lecture yesterday, you remember our criterion was that there should be a map of norm 1, an inclusion of norm 1 from this space to this space. There was a family of C-star algebra, but it could be countable, and all the algebras could be script C. So that boils down to that. And this is true, of course, because in this case, the max is the same as the min. And for the minimal tensor product, we've remarked yesterday that this was an obvious, this property star is obvious for the min norm. Okay, so you see, because I have constructed this counterexample very much by local properties, I conjecture that actually some of the examples fail the LP. And I have the last statement that by which I will conclude, a statement which is a statement of my failure, because I have, unfortunately not been able to complete my project. My project really has been, for the whole COVID period and until now, to try to show that one of these examples, which has the local lifting property, fails the lifting property. I cannot decide actually whether they have the lifting property or not. But I came to a very strange statement similar to Kierkegaard's, proposition of equivalence of conjectures that you cannot decide. So this is a statement like that. So I don't know if anything is true or false in what I'm listing, but I know that they are equivalent. So the algebras that I construct has the lifting property, just this object, if and only if the implication local lifting implies global lifting holds for any C-star algebra with weak expectation property. And then this statement is also equivalent to saying that there is a completely isometric embedding, call it F, from script C to script C, such that the minimal and maximal norm coincide on FC tensor C. And you see, if the map F was not a completely isometric embedding, but simply if it was surjective or the identity, then that would mean that we have the cone embedding problem as the property number 3. But apparently, this is a weaker statement to just say that we have coincidence of min and max norm, not on the whole of C tensor C, but on a subspace like this, where the first factor is a very good copy of C. So it seems very close to showing that actually this implication, local lifting implies global lifting, perhaps simply is equivalent to the cone embedding problem. But even this I cannot show. I can only show you this theorem. If I can progress more and show that it implies the cone embedding problem, then at least the problem will be decided whether local lifting implies global lifting, provided one believes the correctness or one verifies the correctness of the preprint with the 5 authors that announced the solution of the cone embedding problem. Thank you very much. Again, apologies for being long. I have the excuse, I can claim I have the excuse that I've been slightly interrupted, but thank you very much. I'm very grateful for your attention.
Oh, thank you. Questions? I think Professor Sophie may want to.
Yeah, I just want to, slightly modify my question. Professor Pisier, are you getting me?
Yes, fine.
So it could be like this. Is it true that a von Neumann algebra is the range of a completely contractive map from its bidual?
Yes.
Oh, I see. Is that so?
Yes, this is true for any dual, right? Well, yes, there are any dual operator space. Yes.
I see. Okay. So is it easy to verify or?
Well, it is basically, you could say, that, well, the Banach space statement, right? You're asking completely contractive, right? But you agree to the contractive case, right? So you agree to the contractive case, and now you apply your question to Mn with values in A, and you do, the identifications, natural identifications, bidual of MNA with Mn with values in the bidual. And then that will tell you that you have, if you can see it like that anyway. It tells you you have, for each N, you have a good projection that is, Mn contractive, but then you can take some weak star limit, and the weak star limit will be completely contractive. I mean, that's a strange way to do it, but that was just to convince you.
All right. And there was a related question that I had asked in the chat. Maybe it has a trivial answer. Whether an operator Hilbert space could be injective. Operator Hilbert space.
Hilbert space. Yes. So Hilbert space. So this is yes. So row and column spaces are Hilbertian. So as Banach spaces, and row and column space are injective indeed. So this is the papers of Rouen on injective operator spaces that study this, and they have been, they have been characterized. So basically, the idea is that row and column, in fact, is not so different from B of H, because this is B of H with values. This is B of H K with K and H different. So in other words, this is like rectangular matrices. And so rectangular matrices are just as injective as square matrices, okay? So that's the idea. But they've been characterized. But it gives you, some of them are Hilbertian. And then, I proved something about that. Let me see, what did I prove? I think I proved I think I proved the theorem that The only, if you have an operator space which is reflexive as a Banach space and which is injective, then it must be Hilbertian. I think you should check, but I think I
see.
I think I put something like that long ago.
Okay.
So yeah, that's the picture.
So any other question? Anybody? Okay, so if no questions, then I would like to thank Professor Pisier for agreeing and delivering these 4 beautiful lectures. I mean, that's as we have said earlier, that this basically is the series is in the name of Professor E.B. Tiwari, and which will be an annual event. And we are really grateful to you, Professor Pisier. So we thank you for agreeing and delivering this series. And now all the talks, the video recording will be uploaded in the same website which we are going to maintain. So in the later stage, if you want to see again and again these talks, so that will be helpful for you. So now I would like to thank Professor Pisier again, and let's give him a big round of